We tend to think of progress as a straight line. Old methods seem primitive, and new methods seem better. But when it comes to timber construction, that assumption falls apart. Medieval timber-framed buildings are still standing across Europe. Manor houses, barns, churches, and homes, some dating back to the 12th century. These structures have outlasted countless modern buildings that were supposedly built with superior technology. The secret lies in how medieval carpenters understood wood, joints, and structural flexibility. And it turns out their methods are specifically excellent at surviving earthquakes. Modern construction relies heavily on rigid connections. We bolt things together, we use nails and metal fasteners, and we create structures that are stiff and unyielding. That seems like strength. It is not. When an earthquake hits, rigid structures have nowhere to go. The energy travels through the building with nothing to absorb it. Connections fail. Walls crack. The whole thing can come down. Conventional framing joins members using nails or other mechanical fasteners. These connections are strong under normal conditions, but they create stress points. When the ground shakes, those stress points become failure points. Modern wood itself has problems too. Today's lumber comes from fast-growing plantations. These trees grow as tall in 20 years as they used to in 100. Fast growth means loose structure. The wood is porous like a sponge. Water penetrates, fungi settle, and the wood rots from the inside out. The industry solution is pressure impregnation, pumping wood full of chemicals like copper, chromium, and arsenic. These treatments work temporarily, but they wash out over time. They do not address the fundamental structural weakness. Medieval builders faced none of these problems. They used slow-growth hardwood, primarily oak, and they connected it in ways that actually get stronger under stress. Medieval timber framing uses an entirely different philosophy. Instead of fighting movement, it accommodates movement. The primary joinery method is the mortise and tenon joint. This involves a stub, the tenon, fitting into a hole, the mortise. Then a wooden peg is inserted to strengthen and stabilize the connection. No nails, no metal, just wood, interlocking with wood. But here is where it gets clever. Medieval carpenters used a technique called drawboring. They would bore a hole through both walls of the mortise. Then they would bore a separate hole through the tenon, but that hole was slightly offset, closer to the shoulder. When they assembled the joint and drove a tapered peg through those offset holes, the peg drew the joint permanently tight. This creates what woodworkers call a mechanical interlock. The joint does not rely on glue or fasteners to hold together. The geometry itself keeps it locked. The benefits for earthquake survival are substantial. These pegged joints allow for a surprising degree of flexibility in the movement of the frame. Evidence of this is clearly visible in the many old buildings we see today, which are leaning all over the place, some in quite an alarming manner, without actually falling down. That flexibility is exactly what you want in an earthquake. The building can sway and shift without breaking. The joints absorb energy instead of transferring it. The whole structure moves as a unit rather than tearing itself apart. Medieval carpenters developed an entire toolkit of joints for different structural needs. Scarf joints enabled the joining of two beams end to end, when available timber could not provide the required length. These were not simple butt joints. They featured interlocking tapered ends that resisted both tension and compression. One variation, called the stop-splayed scarf or the bolt of lightning, used geometric shapes that locked together like puzzle pieces. The dovetail joint, known from furniture in Egyptian tombs and Chinese imperial palaces, was used to connect roof purlins and floor joists. The diagonally cut fingers resemble the tail feathers of a dove. This shape holds the connection after assembly and makes it very difficult to pull apart. Knee braces, slanting beams between horizontal and vertical members, stiffened corners against racking. These triangulated connections add rigidity where it is needed, while allowing flexibility elsewhere. The interlocking nature of these joints distributes weight evenly, reducing stress on any single point. This is one reason timber framing remains a trusted method for heavy load structures, and it is why these buildings handle seismic stress so well. In North America, Heavy timber construction is classified as Building Code Type 4, a special class that recognizes the inherent fire resistance of large timber and its ability to retain structural capacity even in fire situations. The same mass that resists fire also resists earthquake damage. Material quality mattered enormously to medieval builders. The predominant timber species for structural purposes was oak. It is an immensely strong, durable, and long-grained timber. Medieval foresters and carpenters had an intrinsic understanding of the trees they used. The most prized part of the trunk was the inner section called heartwood. It contains the densest and most durable timber. The outer sapwood, which distributes food and water for growth, is far less dense and more susceptible to insect attack and fungal decay. Medieval carpenters knew to use heartwood for structural members. They also understood wood preservation without chemicals. Linseed oil extracted from flax seeds penetrates deep into wood. It does not clog the pores, but it hardens inside them. The wood remains flexible, and it becomes water repellent. German carpenters treated their half-timbered houses with linseed oil. These houses are still standing today. After 500, 600, 700 years, the wooden beams have darkened, but they remain in perfect condition. Vikings soaked their ship planks in boiled linseed oil. Archaeologists have excavated Viking ships buried for over 1,000 years, where the wood was still so well preserved that the original linseed oil treatment could be detected.